Look at your hand. Go on. Hold it there in the light. Turn it over. See the lines etched into the palm, the creases at the knuckles, the architecture of the bones beneath the skin. It feels solid, does it not? It feels real. It is a thing, a definite object in a world of other definite objects. You can wrap your knuckles on a wooden table, and the table pushes back, solid against solid. This is the first and most fundamental truth of your experience. This truth is a lie. It is a beautiful, elaborate, and utterly convincing illusion, a story whispered to you by your senses from the moment you were born. A necessary fiction that allows you to navigate the world. But it is a fiction nonetheless. Because beneath the surface of that hand, beneath the skin, past the cells, deeper than the molecules, you are not solid at all. You are a storm. You are a vast and echoing emptiness, a void punctuated by infinitesimal sparks of frantic energy. If you could shrink yourself down into the heart of a single atom of carbon in your own fingertip, the experience would not be one of substance, but of dizzying scale and space. The nucleus of that atom, the supposed core of its reality, would be a speck of unimaginable density, more than a football field away in this new, microscopic perspective. And orbiting that distant, lonely sun would be nothing. Not planets, not little balls of matter. There would only be a haze, a cloud, a shimmering, wraith-like region of pure potential, a place where a particle we call an electron might be. Not where it is, but where it could be. It exists as a smear of probability, a ghost haunting the vast, empty cathedral of its own atom. You are composed of trillions upon trillions of these cathedrals of emptiness. So why do you feel solid? Why does your hand not pass straight through the equally empty table? What is holding this grand illusion together? It is not substance. It is force. It is a set of invisible rules, a conversation of pure energy that weaves the void into the tapestry of the world you perceive. It is the electromagnetic repulsion between the electron ghosts in your hand and the electron ghosts in the table, a command that shouts "no closer" across the nothingness, creating the sensation of touch. But even that is not the deepest truth. It is only the first layer of the illusion peeled back. To find the real foundation of your solidity, of all solidity, we must go deeper. We must journey past the electron's hazy shell into that impossibly dense heart of the atom, the nucleus. And then we must go deeper still. We must commit an act of forbidden violence. We must try to shatter the unshatterable. We must look for the prisoners. For inside the familiar protons and neutrons that give your matter its weight, there are things that have never been seen alone. Things that have never, in the entire 14 billion year history of the cosmos, existed in isolation. They are particles that are born in groups and die in groups, forever bound to one another by a force so strange, so powerful, it borders on the paradoxical. They're not things in the way you understand things. They are more like ideas. They are notes in a chord that can never be played separately. They are foundational, essential, and in a way, not entirely real. They're the quarks, and they're the beginning of a story that undoes everything you think you know about what it means for something to be. To understand this, we must go back. We must travel in time to a moment of beautiful confusion in the history of science. The year is 1964. But the story truly begins in the decade before. The world of physics was a mess. A glorious, exhilarating, and deeply frustrating mess. After the stark simplicities of the Second World War and the dawn of the atomic age, scientists had turned their new, powerful tools inward, using particle accelerators like giant microscopes to peer into the heart of matter. They expected to find a simple, elegant clockwork, a few fundamental gears and springs from which everything was made. Nature, it turned out, had other plans. What they found instead was a zoo, a bewildering, chaotic menagerie of new particles. Every time they smashed protons together with more energy, new entities with bizarre names and even more bizarre properties would spill out from the wreckage. There were pions and kaons, lambdas and sigmas, deltas and xis. Hundreds of them. They were all unstable, flashing into existence for fractions of a second before decaying into other, more familiar particles. It was chaos. There was no rhyme or reason. The elegant universe of Einstein and Bohr was starting to look like a cluttered attic, full of cosmic junk. Where was the order? Where was the pattern? Physicists felt lost in a wilderness of their own creation. It seemed as though the deeper they looked, the more complicated reality became, the very opposite of what they had hoped for. Into this chaos stepped a man named Murray Gell-Mann. He was a scientist, of course, but he was also something of a poet, a linguist, a man fascinated by patterns, by language, by the hidden grammar of the world. He looked upon the particle zoo not with despair, but with the keen eye of a naturalist discovering a new ecosystem. He believed there had to be a deeper structure, a kind of periodic table for these ephemeral flashes of existence. He began to sort them. He grouped them by their properties, their mass, their electric charge, their spin, and as he did, a ghostly pattern began to emerge from the noise. He found he could arrange these disparate particles into beautiful, symmetrical, geometric shapes. Little families of 8, little families of 10. He called this classification scheme the Eightfold Way, a nod to the noble path of Buddhism. It was a name that hinted at a deeper, almost spiritual order underlying the messy reality of a laboratory. It was beautiful, it was elegant, and it worked. His system could not only organize the known particles, but also predict the existence of a new one, the omega- particle. He described its properties, its mass, its charge, and told the experimenters where to look. In 1964, they found it, exactly as he had predicted. It was a stunning triumph, a moment of sublime order imposed upon chaos. But this triumph created an even deeper paradox. The patterns were real. The symmetry was undeniable. But what did it mean? Why did these particles obey this hidden numerology? It was like discovering that all the animals in a zoo could be arranged into perfect triangles and hexagons based on their weight and color. It would imply they were not fundamental at all, but were instead made of smaller, constituent parts. Gell-Mann, along with another physicist, George Zweig, who was working independently, took the brave and seemingly absurd next step. He proposed that all of these particles in the zoo, the protons, the neutrons, all the hundreds of others, were not fundamental. They were composite objects. They were made of something smaller. He needed a name for these hypothetical building blocks. The mathematics required them to come in threes. The name, he decided, should be playful, almost nonsensical, to reflect the strangeness of the idea. He found it in a line from James Joyce's baffling, dreamlike novel, Finnegan's Wake. 3 quarks from Mustermark. Quark. The word meant nothing. It was a sound, a piece of literary whimsy. It was the perfect name for a particle that might not even be real. Because that was the problem. A gigantic, gaping problem. If protons were made of 3 quarks, and all these other particles were made of quarks, then where were they? Scientists looked. They smashed atoms with more and more power, hoping to chip a single quark off a proton, to see it fly free and prove its existence. They sifted through the debris of cosmic ray collisions. They searched everywhere, and they found nothing. Not a quark, not a hint of a quark, not a shadow. It was as if the universe was actively hiding them. The idea became a kind of scientific embarrassment, a mathematical trick. The quarks were seen as a convenient fiction, a bookkeeping device that explained the patterns but had no physical reality. Gell-Mann himself was deeply cautious, suggesting they might be confined, forever trapped inside their parent particles. But to most, it seemed simpler to assume they just weren't there. Reality, it seemed, was made of patterns, but the cause of those patterns was a ghost, a phantom that lived only in the equations on a blackboard. Science had solved a riddle only to be confronted by an enigma. How can the foundation of reality be something that cannot exist on its own? It was a question that would take another decade of struggle and a revolution in thinking to even begin to answer. The answer, when it came, was not an object. It was a force, a new kind of force, more powerful, and more bizarre than any that had come before it. And to understand it, we must first learn the strange new language it speaks, a language of flavors and of colors. Let us begin with the taxonomy of the strange. The Cork family portrait is not small. Gelman initially proposed 3, but as the years went on and energies and accelerators grew, it became clear there were more. Today, we know there are 6, and in the poetic tradition of their naming, they are not given technical, boring labels. They are given flavors. There is no taste involved, of course. It is just a name, a way to categorize them into 3 pairs or generations. The first generation is the stuff of our world. The up quark and the down quark. They're the lightest, the most stable, the bread and butter of the cosmos. A proton, the heart of a hydrogen atom, is 2 UPS and 1 down. A neutron is 2 downs and 1 up. With just these 2 flavors and the electron, you can build the entire periodic table. You can build stars, planets, and people. It is a world of magnificent simplicity. But the universe is not content with simplicity. The second generation is stranger. It consists of the charm quark and the strange quark. The strange quark earned its name because the particles it formed seemed to live for far too long. In the frantic world of subatomic physics, where lifetimes are measured in trillions of a second, these strange particles lingered for a whole 100th of a billionth of a second longer than expected, as if they were reluctant to decay. It was a clue, a hint that some new rule of nature was at play. Its partner, the charm quark, was predicted to exist for reasons of pure symmetry. Its discovery in 1974 was so momentous, a confirmation of the entire quark model, that it was dubbed the November Revolution. It solved so many theoretical puzzles at once that its existence was seen as, well, charming. Then there is the third generation, the heavyweights, the top quark and the bottom quark. These are fantastically massive. The top quark, discovered only in 1995, is as heavy as an entire atom of gold, yet it is a fundamental particle with no size at all. It is so unstable it decays almost instantly, before it even has time to form a particle with other quarks. It is a fleeting, gargantuan ghost at the edge of existence. Its partner, the bottom quark, or sometimes beauty, is its slightly less massive sibling. 6 flavors. 3 generations of increasing mass and instability. Our entire stable, solid world is made only of the first, lightest generation. The other 2 are like exotic, short-lived relatives who appear only at very high-energy family reunions, before vanishing again. But flavor is only half the story. The true mystery, the key to the prison that holds them, lies in another property. A property that has nothing to do with sight, but which physicists, in another moment of poetic whimsy, decided to call color. Every quark, of every flavor, carries a second kind of charge. Not electric charge, but something new. There are 3 types of this new charge, and they're called red, green, and blue. Let this be absolutely clear. This has nothing to do with the colors you see with your eyes. A red quark is not colored red. It is a metaphor, and it is perhaps the most important metaphor in all of modern physics. It is an analogy for how these charges must combine. Just as the 3 primary colors of light, red, green, and blue, combine to make neutral, white light, the color charges of quarks must combine in a specific way. The universe, it seems, has a rule, an aesthetic preference. It despises seeing a single color on its own. It only permits objects that are color neutral or white. This is the rule of the prison. You can have a particle made of 3 quarks, but only if one is red, one is green, and one is blue. The combination is color neutral. This is what a proton is. This is what a neutron is. They are called baryons from the Greek word for heavy. Or you can have a particle made of a quark and an antiquark. An antiquark has an anti-color. A red quark and an anti-red antiquark, for instance, cancel each other out to become color neutral. These particles are called mesons from the Greek for middle. But you can never, ever have a single red quark on its own, or a green one, or a blue one. The universe forbids it. Any particle that exists freely, that can be observed in a laboratory, must be color neutral. It must be white. This is why the search for a free quark always failed. You cannot find one for the same reason you cannot find a single, isolated north pole of a magnet. If you cut a bar magnet in half, you do not get a separate north and a south pole. You get two new, smaller magnets, each with its own north and south. The universe insists on this duality. In the same way, the universe insists on color neutrality. But why? What enforces this bizarre rule? What is the force that acts as the prison warden? To answer that, we must meet the messenger, the carrier of this force. We must meet the gluon. The force is called the strong nuclear force, and the gluon is the particle that carries it, binding the quarks together. The name is wonderfully direct. They literally glue matter together. And here, the story moves from the strange to the truly mind-bending. Think of the force you know best, electromagnetism. It's carried by a messenger particle, the photon. A photon is a particle of light. It carries the electromagnetic force between, say, two electrons, causing them to repel each other. But the photon itself has no electric charge. It is neutral. It is a messenger that does not feel the message it carries. This means photons do not interact with each other directly. Two beams of light can pass right through one another without scattering. The strong force is different, profoundly different. The gluons that carry the force between quarks do feel the force themselves. Remember the color charge? Red, green, and blue. Well, gluons have color charge too. They have a combination of a color and an anticolor. There is a red anti-green gluon, for instance. Because gluons themselves are colored, they interact with each other. They stick to each other. Imagine trying to send a letter, but the postage stamps are all covered in superglue. The letters would stick to the mail carrier would stick to the mailbox, and other mail carriers would stick to them. It would be a chaotic, sticky mess. This is the world inside a proton. A frantic, seething, sticky ball of quarks and gluons, constantly exchanging color, constantly interacting with each other. A quark can change its color by emitting a gluon. A red quark can become a blue quark by emitting a red and a blue gluon. The proton isn't a static arrangement of three little balls. It's a dynamic, violent dance of quantum chromodynamics. That is the formal name for this theory, QCD. And it is this self-interaction, this stickiness of the gluons, that gives rise to the most counterintuitive property of the strong force, and the ultimate reason for the prison of confinement. With all other forces in nature, like gravity or electromagnetism, the force gets weaker with distance. The Earth's gravity pulls on you less the farther you travel into space. A magnet's pull weakens as you move it away. The strong force does the exact opposite. The force between two quarks gets stronger as you try to pull them apart. Think of it like an unbreakable cosmic rubber band. When the quarks are close together inside a proton, they barely feel each other. They jiggle around in a state of what's called asymptotic freedom. They are free as long as they stay in their room. But try to pull one of them out. Try to stretch that rubber band. The force resisting you does not weaken. It remains constant and powerful, no matter how far you pull. You pour more and more energy into stretching the band, into the gluon field between the two quarks. The energy builds and builds and builds, stretching out into a thin tube of force. And then something extraordinary happens. The energy you have poured into the gluon field becomes so immense that it becomes cheaper, from the universe's point of view, to do something else. According to Einstein's most famous equation, E equals mc squared, energy and mass are two sides of the same coin. Put enough energy into a system, and you can create new particles out of the pure vacuum. The rubber band snaps, but it does not release the quark. Instead, the energy in the stretched band spontaneously transforms into a new quark and a new antiquark. The new antiquark pairs with the quark you were trying to pull out, forming a color-neutral meson. The new quark stays behind with the original two, forming a color-neutral baryon once more. You started with one proton. You try to pull one quark out. and you ended up with a proton and a brand new meson. You did not liberate a prisoner. You created more of them. This is confinement. It is absolute. The force is literally unbreakable. Any attempt to break it only provides the energy to create new particles that maintain the rule of color neutrality. The universe will create new matter from nothingness to enforce its law. So how could we ever know this is true? If we can't see a quark, how do we know it's there? We see its shadow. We see the evidence of its violence. The proof came from a series of landmark experiments in the late 1960s and early 1970s at the Stanford Linear Accelerator Center, or SLAC. The experiment was a masterpiece of indirect observation. The idea was simple in concept, brutal in execution. They would take a proton, a thing they wanted to understand, and shoot at it. Their bullets were electrons, accelerated to nearly the speed of light. These electrons were small enough and energetic enough to probe the inner structure of the proton itself. If the proton were a soft, uniform ball of charge, like a bag of Jell-O, the electrons would pass through it or be deflected gently. But that is not what happened. Every so often, an electron would be violently knocked aside, ricocheting at a huge angle, as if it had struck something small, hard, and solid inside the proton. It was like firing a rifle into a bale of cotton and hearing the occasional ping of a ricochet. It told you there were pebbles or marbles hidden inside. These scattering patterns, a technique called deep inelastic scattering, were the shadows of the quarks on the wall of the laboratory. They were the first experimental fingerprints of these confined entities. We could not see the quark, but we could hit it. We could confirm its existence by its refusal to get out of the way. Later, at other accelerators, scientists would find even more direct evidence. When they collided particles at incredibly high energies, they would sometimes see jets of new particles streaming out in opposite directions. These jets were the footprints of a quark and an antiquark, created from the vacuum, flying apart for a brief moment before the strong force asserted itself, snapping the rubber band and creating a shower of new, color-neutral hadrons in their wake. We see the debris from the failed prison break. We see the consequences of the unbreakable bond. We never see the prisoner, only the evidence of their eternal, failed struggle for freedom. And here we must pause. We must step back from the physics and truly consider the sheer, unadulterated strangeness of what the universe has revealed to us. This is not just a new force. This is a new kind of reality. The phenomenon of confinement is a profound challenge to our deepest intuitions about the world. It is a violation of one of the most fundamental principles of our logic, reductionism. The idea of reductionism is simple and powerful. It has guided Western thought for millennia. It is the belief that you can understand a complex system by breaking it down into its constituent parts. A house is made of bricks. A clock is made of gears. A book is made of chapters, which are made of sentences, which are made of words, which are made of letters. We have applied this logic to the universe itself. Society is made of people. People are made of organs. Organs are made of cells. Cells are made of molecules. Molecules are made of atoms. Atoms are made of electrons, protons, and neutrons. And protons and neutrons are made of quarks. And here, the ladder of reductionism, the chain of made of, breaks. It shatters against the wall of confinement. A proton is made of quarks, but you cannot take the quarks out of the proton. Read that sentence again. Let it sink into the bedrock of your understanding. It is a statement that should feel impossible. How can a thing be composed of parts that have no independent existence? It is like saying a word is made of letters, but those letters vanish in a meaninglessness if you try to write them down individually. It is like saying a chord is made of notes, but the notes themselves cannot be played alone. They can only exist together. This is not an analogy. According to the theory of quantum chromodynamics, this is the literal truth of our physical reality. The fundamental components of the matter that makes you cannot exist. Not alone. Their very being is relational. A quark is not a thing in itself. It is a participant in a pattern. Its reality is defined entirely by its connection to other quarks. What does this do to our concept of a fundamental particle? We have always imagined this to be the end of the road, the final, indivisible Lego brick of creation. A tiny, solid ball. But a quark is not that. A quark is a ghost, a prisoner, a mathematical necessity that the universe conspires to hide from plain view. This conspiracy is active. It is dynamic, and it involves you, the observer. Consider again the act of trying to see a single quark. You pull on it with immense energy. You are the observer attempting to make a measurement. You are asking the universe a question: is there a single red quark here? And the universe answers. But its answer is not yes or no. Its answer is to change the experiment. In response to your question, reality creates new matter. It creates a quark-anti-quark pair from the energy of your query, ensuring the answer is always no. There is only this color-neutral meson and this color-neutral baryon. This is a profound echo of the strangeness at the heart of all quantum mechanics, but with a creative twist. In the more famous double-slit experiment, the act of observing which path a particle takes forces it to abandon its wave-like nature and behave like a particle. The observation changes the behavior. But here, in the realm of the strong force, the act of observation doesn't just change behavior. It changes being. It creates existence. Your attempt to isolate a piece of reality fundamentally alters reality by adding new pieces to it. It suggests a universe that is not a static stage upon which events unfold, but a dynamic, responsive dialogue. A conversation between the rules of physics and the questions we ask of them. And in this conversation, some questions are simply forbidden. Not because we lack the technology to ask them, but because the grammar of the cosmos itself makes them nonsensical. Asking to see a single quark is like asking to see the meaning of a sentence by looking only at the letter T. The question itself misunderstands the nature of what it is examining. Meaning, like a proton, is an emergent property of a collection of things that are themselves meaningless in isolation. This is unsettling. It should be. It tears down the comfortable, mechanistic view of the world and replaces it with something fluid, relational, and deeply mysterious. The clockwork universe is gone. In its place is a web of relationships, where the connections between things may be more fundamental than the things themselves. So, what do you fit into this? You, sitting there, feeling solid, feeling definite. You're made of this. Every proton in every atom of your body, every neutron that gives you mass, is a tiny, seething prison. Each one is a frantic dance of three quarks, bound by a shimmering, sticky web of gluons. A universe of violent, beautiful, inescapable connection, repeated trillions upon trillions of times to form the placid and stable object you call yourself. Your solidity is not the solidity of a rock. It is the solidity of a vortex. It is the stability of a standing wave. It is the integrity of a story, held together by the unbreakable grammar of the strong force. You are built from ghosts. You are a collection of prisoners who, by their very confinement, create the structure that allows you to exist. The force that forbids them from being seen is the very same force that holds you together, that gives you substance, that allows your hand to rest upon a table. What does this mean for your sense of self? Your boundaries? We think of ourselves as discrete individuals. I begin here, and the world begins there. But the physics that constitutes you is one of relationships, of inseparable parts, of wholes that are somehow more real than their components. Could this be a metaphor for something deeper? You are not just a collection of particles. You are a pattern, an arrangement, an impossibly complex set of relationships, processing information, experiencing the world. You are a stable resonance in the quantum fields, a color-neutral entity in a cosmic sense. And this leads us to the ultimate, perhaps unanswerable, questions. What then is truly real? Ask yourself the question one more time. Is a quark real? It has mass. It has charge. It has spin. It deflects electrons. It leaves jets of particles in its wake. By every scientific measure, It has all the properties of a real thing. And yet, it cannot be isolated. It cannot be put in a bottle. It has no independent existence. Its reality is conditional. It is real only insofar as it is in relationship with other quarks. So, which is more fundamental? The particle or the relationship? The quark or the unbreakable bond of the strong force? Quantum chromodynamics suggests that the relationship is what's primary. The universe, at its deepest level, is not a collection of objects. It is a collection of interactions. It is a verb, not a noun. Reality is not a set of things. It is a set of rules. The strong force is one of those rules. A very, very powerful one. And a quark is simply what we call a place where that rule is being applied. This shifts our entire perception of existence. We are no longer explorers discovering a pre-existing territory of matter. We are deciphering a text. We are learning the grammar of a cosmic language where the meaning is held not in the letters, but in the way they are bound together into words. The proton is a word. The neutron is a word. You're a library, an epic poem written in the language of confinement. And perhaps, in a leap of speculation, this strange logic of the subatomic world echoes in the grandest mystery of all, the mystery of consciousness. Think of your own mind, your own subjective experience of being. It is a unified whole, is it not? You experience the world as a single, seamless reality. You don't experience the firing of individual neurons. You don't experience the raw data from your optic nerve. You experience seeing a red bird. You cannot separate this seeing from the redness from the birdness. They are bound together in a single, indivisible moment of perception, just as the quarks in a proton are bound into an indivisible whole. Could it be that consciousness is another kind of emergent property, a kind of confinement, a complex, self-referential pattern whose constituent parts have no meaning on their own? You can't break down the experience of love or sadness into smaller, more fundamental feelings. The experience is the whole. The whole is the only thing that is real. Perhaps the unified nature of your own self, your I, is a macroscopic reflection of the same principle that holds a proton together, a stable, color-neutral state in the impossibly complex neural field of your brain, an unbreakable relationship between billions of processing elements, giving rise to a new kind of whole that cannot be reduced. This is speculation. It is philosophy, born from the strange truths of physics. It is the human mind trying to find a pattern in the patterns. But isn't that what science has always been? We return, then, to the beginning, to your hand, to the feeling of its solidity. The lie is still there. It feels just as real. But now you know what lies beneath it. Not emptiness, not exactly, but a vibrant, dynamic web of force. A set of rules being enforced with absolute, creative power. The question we started with was, what are you made of? The simple answer is atoms. The deeper answer is electrons and nuclei. The even deeper answer is electrons and quarks. But the truest answer might be something else entirely. You are made of relationships. You are made of an unbreakable bond. You are composed of things that cannot exist without each other, and in their togetherness, they create the steadfast reality you inhabit. You are a testament to the idea that the whole could be profoundly more than the sum of its parts, especially when the parts themselves are forbidden to be free. So are quarks real? Perhaps the question itself is the illusion. It's a question born from a classical, reductionist mindset that the universe, at its most fundamental level, has rejected. It is like asking if the note C is more real than the C major chord. The question misses the point. The point is the harmony. The point is the music. The strong force is the music of matter. The quarks and gluons are the notes and the rhythms. And the universe is the symphony that results. A symphony so vast, so complex, that in one small corner of it, it has given rise to a creature made of that same music, a creature that has learned to listen to the score. Look at your hand one last time. It is not a thing. It is an event. It is a performance. It is a 14-billion-year-old story of confinement and connection, of unbreakable bonds and emergent beauty. You're not a collection of particles. You are a pattern held together by the poetry of the cosmos. A whisper in the equations made manifest. A question that the universe is asking of itself. And the answer, for now, is simply the breathtaking, solid, and utterly mysterious fact of your own existence.